we have 3 talks, and Thomas is going to be our first one. So please, take it away.
Thank you, Jess, and thanks to the organizers for giving the opportunity to speak here. So I'll talk about a paper called Parameterized Algorithms for Multi-Label Periodic Temporal Graph Realization. This is joint work with Niels Molowitz and Peter Wold. Niels is on Zoom, I believe. And I'm particularly grateful to Niels because he essentially made all the slides. He gave a talk about this at SAND 4 weeks ago, and I've mostly reused them and just modified them a tiny little bit. So what do we do in this work? We study temporal graph realization, and in particular periodic temporal graph realization, which is a problem that was introduced by Globus et al. In also a SAND paper. So what is this problem? You're given a duration matrix D that specify for every pair of vertices the duration of the fastest temporal walk that you want to have between these 2 vertices. And you want a periodic graph, so you also are given a period delta. So that tells you how many time steps you have after which the temporal graph is meant to repeat. And you can also assume that you are given the underlying graph of the temporal graph. Because whenever the duration matrix says 2 vertices should have a walk of duration 1, you know these 2 vertices must be connected by an edge. Whereas if the duration matrix says these 2 vertices, the fastest walk would have duration 2, 3, or 4 or more, then you know these are not connected in the underlying graph. So the underlying graph is simply the set of all edges between vertices where the duration matrix specifies that you want a walk of duration 1. And Globus et al. Studied the problem where you have to assign a single time label to every edge in such a way that the periodic graph with these time labels realizes your given duration matrix. That means for every pair of vertices U and V, the duration of the fastest walk from U to V is exactly the value specified in the input duration matrix. And the duration of a temporal walk, I mean, just like in previous talk, we're looking at strict temporal walks. So a temporal, to get from vertex U to V, you use edges at strictly increasing time steps. And the duration of a walk is the time step of the last edge you use minus the time step of the first edge you use plus 1. So for example, if your input matrix is this, so you have 3 vertices between 1 and 2 and 2 and 3, the distance is 1, so you know your underlying graph is this. And you give a period of 5. Then, so we basically want to assign time labels to these edges and a single time label to every edge to realize this distance matrix. Let's give the edge from U1 to U2 label 1. It doesn't matter which one, we have to give a label. And then to get a distance of 2 from vertex 1 to 3, then we have to assign the second edge a label of 2. Because now the walk from U1 to U3 will use this edge at time 1, this edge at time 2, so the duration of this walk is 2. And the problem is now that the distance matrix also says the walk from vertex 3 to vertex 1 should have duration 2, but actually the walk from U3 to U1, we can use this edge at time 2, but then this edge that has time label 1 will only be available again at time 6. So you have to use that edge at time 6, and that walk will have duration longer than 2. So with a single label for every time edge, we cannot realize that distance matrix here. And in our paper, we generalized that problem to multi-label periodic temporal graph realization. So we say that in addition, you're given a number L, and you're allowed to assign L time labels to every edge. So lambda is no longer a function that maps each edge to a single time label, but we can give up to L time labels to every edge. And now if you look at the same input, we could assign label 1 to this edge, label 2 to this edge, and then label 3 to the first edge. So now we do indeed have a temporal journey of duration 2 from vertex 1 to 3, but also from 3 to 1. So this distance matrix or duration matrix is realizable by this graph. And so the question we want to solve in general is, given such a duration matrix, does there exist a temporal graph realizing it with at most L labels per edge? Any questions about the problem we are looking at? So in their paper, Globus et al. Showed the problem for a single label per edge is NP hard for every period greater or equal to 3. And we generalize that to the multi-label problem and show that even for small distances. So Dmax is the maximum duration in the matrix. So even if for every pair of vertices you want a walk of duration at most 3, and you have a period of length 6, then for any L greater or equal 1, the multi-label periodic temporal graph realization problem is NP hard, even on a very simple underlying graph, namely a split graph where you have an independent set and a clique connected by some edges. And as a positive result, Thomas et al. Showed that a periodic temporal graph realization is polynomial for trees. And the most sophisticated result they have in their paper is that it's actually fixed parameter tractable with respect to the feedback edge number. So if the underlying graph is a tree, the feedback edge number is 0. But even if you have to remove a small number of edges to get a tree, the problem is FPT for that parameter. And we show that this no longer holds for the multi-label version. So for any number of labels that is at least 5, we show that multi-label periodic temporal graph realization is NP hard already on stars. So very simple trees, namely stars, it's already NP hard for the multi-label case. And I'll first give you some ideas of the reduction to prove this. So it's a reduction from vertex cover, actually some restricted types of instances of vertex cover. So you're given a graph and you want to find a minimum number of vertices that cover all edges. So for example, for this graph, we want to decide is there vertex cover of size 3? And yes, there is. So choosing vertices U1, U5, and U7, you have, for every edge, you have at least one endpoint in your vertex cover. So this is the vertex cover. The temporal graph multi-label realization problem that we generate as a center and a leaf for each of the vertices of this vertex cover instance. And the distances we want to achieve is we want to have a distance of 2 for every pair of vertices that have an edge in the vertex cover instance, and a distance of n squared, so number of vertices squared, if it's not an edge of the vertex cover instance. And the period we allow you to use is roughly k plus 2 times n squared. And to give you an idea, so this is this long period. And first of all, because for every pair of vertices, we definitely want to have a journey of duration n squared. We make a time step 1 and a time step n squared, essentially all the edges active. So the set of vertices that are written above the line here means which edges to the center are active in that set. So you can assign time level 1 and time level n squared to all these edges. Then this will realize a temporal journey of duration n squared between any pair of vertices. So all that's left to do is realize duration 2 for every pair of vertices that are connected by an edge. And what you can do is basically every n squared steps, you can use 3 time steps to create journeys of duration 2 for all edges incident to a single vertex. So if you want to realize distance 2 for all edges incident to vertex U1, you let the edge to U1 be active in one time step, the edge to U2 and U5 be active in the next time step, and then again the edge to U1 between the center and U1 active in the next time step. So in the first 2 of these 3 time steps, you can get from U1 to all its neighbors U2 with a journey of duration 2. And between the second and the third step, you can get between each neighbor of U1 and U1 with a journey of duration 2. And so basically, you do this every n squared time step. You use 3 time steps to create distance 2 journeys or duration 2 journeys for all edges incident to one vertex. And since the total length of the period you have is k plus 2 times n squared, that's just enough to realize all edges if and only if there's a vertex cover of size k. So there are some technical details in the reduction, but this is the main idea. So I hope that's clear. And in the rest of the talk, let's talk about positive results. So first of all, the hardness we have shown for the multi-label problem means that there's no hope for FPT algorithms if your parameter is number of labels plus vertex cover of the underlying graph. or number of labels per time edge plus the maximum distance or things like that. So we consider larger parameter combinations. So in particular, we can show if you use as parameter n the number of vertices, then we can have an FPT algorithm for that parameter. And you may think n is a huge parameter. I mean, number of vertices, what can there still be interesting to do? But I mean, the period could be much larger than n. The distances you want to create could be much larger than n. So even if n is the parameter, it's not obvious how to get an FPT algorithm. And we also have an FPT algorithm for vertex cover plus length of the period as parameter. And we also have an FPT algorithm, and especially a polynomial kernel, if the parameter is the number of non-universal vertices plus the maximum distance in your input matrix. And so let's first talk a little bit about this FPT algorithm for parameter n. So first an observation, how many labels might we have to assign to an edge? So if this number of labels that we are allowed by the input instance is larger than n squared, we never have to use so many labels. It's always enough to assign at most n squared labels to an edge, because you need to realize only n squared distances. And so for realizing a distance between two vertices, you might use an edge once. And that means for each of these n squared distances you realize, you might want to assign a label to the edge, but you'll never have a reason to assign more than n squared labels. So if your input parameter L is larger than n squared, you can just reduce it to n squared without any loss, without changing whether the instance is a yes instance or a no instance. So there exists a solution that has at most number of edges times L many time edges. And that means in particular the number of non-empty snapshots, so time steps where the graph has at least one edge, will be at most n squared times L, which is at most n to the 4. So even if your period is much, much larger, exponential in n, the number of time steps where you actually put an edge will be at most n to the 4. And since n is a parameter, we can actually guess what these non-empty snapshots look like. So kind of the number of possibilities for up to n to the 4 non-empty snapshots is bounded by a function of n, and therefore we can just enumerate all possibilities for what these non-empty snapshots are. So this example, these would be the non-empty snapshot for that solution. And there's at most n to the 4 of them, and we can just guess them by enumeration. And that will take a huge running time, n to the O of n to the 4, but since n is our parameter, that's fine. And then we need to decide for one such choice of number of non-empty snapshots, to what time steps do we actually assign to these snapshots. So basically we need to decide how many empty snapshots do we put in between each of these non-empty ones. And for that, we use an integer linear program that has function of n many variables. So it can be solved in FPT time with respect to the number of variables. And from this, we get that multi-label periodic temporal graph realization can be solved in n to the O of n to the 4 time. And I'll talk briefly about that ILP. So we have, let's say we have guessed our L non-empty snapshots. We want to assign them to time steps between 1 and delta, so that the temporal graph with those snapshots of those time steps realizes the duration matrix. So we have a variable ti, which is the time step that we use for the ith snapshot. In addition, we can guess for every fair uv, which of these L non-empty snapshots is the one where the journey that realizes the duration of the walk from u to v starts. And we can calculate for every pair of vertices and every starting snapshot the shortest UV journey that starts in the ith snapshot, at which time can it reach V the earliest, so that will be the J layer or snapshot, Z periods later. And then the ILP simply has these constraints. So the bottom 3 ones, let's say, okay, the time step for the first layer should be greater or equal 1. Then each the ith layer must be at least one time step later than the I minus one snapshot or layer, and the last snapshot must be before period delta. And then we have two constraints. So one says for every UV pair, the length of the journey from U to V that starts in the SUV snapshot must exactly be equal to the duration we want to create. And for every other starting snapshot, the length of the journey must be at least as large as the duration we want to create. It cannot be shorter because then we would get a too short distance. And so basically, if we start in the ith layer, which will be assigned to time step Ti, and it ends in the jth layer, z periods later, then this formula on the left-hand side is exactly the duration of that journey. So this is the ILP we need to solve for every guess of snapshots and SUV values. And in this way, we can solve the problem. The second FPT result we have is for parameter vertex cover number of the underlying graph and period. So here is the underlying graph, and the vertices on the right are meant to be the vertex cover. So the vertices are not in the vertex cover or an independent set, and the size of that vertex cover is part of the parameter. And we basically want to show that such an instance can be reduced to an instance where the number of vertices is at most some function of the vertex cover size and the period. Because once we have that, we can just apply the FPT algorithm on the number of vertices, and that will be an FPT algorithm for this parameter combination. And so first of all, if your vertex cover has size k, then you can partition the vertices of the independent set depending on which vertex cover vertices they are adjacent to. So you have a number of neighborhood classes that is based by 2 to the size of the vertex cover. So all the vertices in each class have the same neighbors in the vertex cover. And in addition, for each of these classes, we can show that you can reduce the size of that class to 2 to the delta times vertex cover number. And how does this work? So this works if one of these classes has more than this number of vertices in it, then there must be 2 that are labeled twins. And labeled twins means that each of, so 2 vertices U and V in the same class are labeled twins. If basically for each of their edges to the vertex cover, both of them have exactly the same set of labels. And label twins correspond to vertices in the input duration matrix that have identical rows and columns. So you can just, if you have 2 such label twins in the same neighborhood class, you can just delete one of them without changing the instance. So this shows, we basically just detect identical rows and columns in the input matrix and remove them. And then we get a vertex kernel of size 2 to the O of delta times vertex cover number. Then we apply the FPT algorithm for number of vertices, and that gives us an FPT algorithm for this parameter combination. And okay, there is, I'm a bit faster than I thought, so in conclusion, what did we do? We developed parameterized algorithms and hardness results for multi-label periodic temporal graph realization. And we also looked at a non-periodic version. So the non-periodic version is, of course, you can ask the same question and say you don't have a delta as input, but you just want to create a standard temporal graph that has some lifetime that realizes your durations. And so many of our results apply to that version as well. And for example, one thing we can do for the non-periodic version is to decide whether to solve the problem if the input matrix has no infinity values. So in the periodic version, it makes sense to assume that there are no infinity values, because in a periodic graph, if you have infinities, it would have to split the graph into independent subproblems that you solve separately. So infinities are kind of don't need to be considered in the periodic version. But in the non-periodic version, you could have an input that says, okay, from U to V, you don't want to have any temporal path at all. But if we assume that there is no such infinity in the input distance matrix, and in addition, between every pair of vertices, you have only a polynomial number of different paths. Then and one more thing, and the number of labels you can assign is essentially as large as you want. That means it's at least n squared. Then we can solve the problem in polynomial time. And what you do there is simply, for every pair of vertices, you check, is there a path where I can realize the distance I want to have for that pair of vertices without creating a path that is too short for any of the pairs that lie on that path. So basically, is there a path from U to V where I can assign time labels so that the path from U to V has exactly the duration I want, but there's no two other vertices on that path for which kind of by accident I create a temporal path that's too short. And we show that that subproblem can be solved kind of in polynomial time with the greedy method. And so if the number of paths you have available for every pair of vertices is small, which holds, for example, if the input is a cycle or something like that, then we can solve the problem in polynomial time simply by realizing for every pair of vertices the distance, then leaving a large gap of empty time steps, realizing the duration for another pair, and doing this for all n squared pairs. And so this hardness we have on stars is for number of labels at least 5. And we know it's in polynomial time for arbitrary trees from the Globas et al. Paper if the number of labels per edge is at least 1. So an obvious question is, what is the complexity if L lies between 2 and 4? And I think Jess is quite good at kind of closing such gaps and finding whether these are also NP-hard or polynomial. So maybe something you or one of your students wants to give a go. And interesting, of course, would be to find other parameters for which the problem is FPT. And one thing we've been thinking about for a while but didn't solve is, so we have an FPT algorithm for parameter n, but we don't know whether there's a polynomial kernel for n. So somehow, so what would be how could the input size be larger than another function of n? That could be if the period is huge, like exponential in n, and if the distances you want to create are exponential. And somehow one might intuitively expect, if you have such huge values for period and distances you want or durations you want to create, maybe there's a method how you can make these smaller and get an equivalent instance so that the whole size of your instance is bounded by a function of n. We feel it might be possible, but it seems quite tricky to do. And then, of course, we look at the model where you need to create exactly the duration that is specified in the input matrix. You could assume that your input matrix is only an upper bound and not the exact duration. So if the input matrix just says, from U to V, I want to have a path of duration at most 10. Then, of course, there's a trivial realization where you make it a clique, and then every pair has a path of duration 1. But then you would probably want to, say, minimize the number of edges in the underlying graph or minimize, I guess that would be the natural objective then. Or you could assume that your distance matrix might have more than 1 values and say, the duration from U to V should be 5 or 7 or 9, but nothing else. So you could say, what's the complexity of this problem? And you could also consider non-strict instead of strict temporal paths. So we've only considered this problem for the strict model, where on every temporal journey, the time labels must be strictly increasing. But there's also work on the non-strict version, where you can, in every time step, follow as many edges as you like in that time step. One could also look at temporal realization problems in the non-strict model. And that was my last slide. So thank you for listening, and I'd be happy to answer any questions.
All right, so I'm going to open the chat, and if there are any questions online, feel free to unmute yourself, or if you don't want to, you can type it in the chat and I'll read it out loud. But in the meantime, while those are appearing, do we have any in the room?
So I might have missed it, but you assume that all of the edges have the same period, right?
We assume here that all the edges have the same period, exactly. There's a global delta, and for every edge, the period is delta.
And if we lift that assumption, your results break? I assume the hardness probably not, but the positive ones might, or?
So they might, I mean, then maybe, I mean, for the N, yeah, we haven't thought about it at all. So it's not, so there is this kind of edge periodic model where every edge has its own period. And for some other problem, that makes things much more difficult because basically the whole graph repeats only after the smallest common multiple of all the edge durations, which can be exponential in the input representation. So we've not looked at the realization problem in the model where every edge specifies its own period. And right now, I wouldn't even be able to make a guess whether any of our results still hold or not. But it's a very interesting direction.
Thank you.
I'll pause and go back and say if there's anyone with a question online, feel free to raise your hand or unmute yourself. Because otherwise I will take the opportunity to ask a question. Okay, so I wanted to ask you about this ILP approach. So it's one that I've only kind of used once or twice. But does it mean, because you're using this ILP approach, it seems like you could include a lot of side constraints that might encode variance if you wanted to? So say...
Yeah, so basically, first of all, I mean, this requires that the number of snapshots, of non-empty snapshots you have is bounded by factor of the parameter.
Yeah.
But once you have that, deciding where in the period to place these snapshots, as long as you don't need extra variables, you could add as many constraints as you like, because as long as the number of variables is bounded, is it the parameter, you can solve it in FPT time.
Yeah, so I was thinking in particular about requiring that a path go via one of a particular small, you know, maybe you color your vertices and I want to say you have to go from here to here, but always at some point via a red vertex or never via a red vertex, right? My train ticket is only good from here to here, avoiding London.
Okay.
I wonder if we could do that without extra variables or with only a small number of extra variables.
I mean, that kind of construct avoiding a vertex, that would more be in this thing that we calculate separately and then use basically these J and Z values in anticipations. They are computed using a separate computation. They check to get from vertex U in that layer as quickly as possible to vertex B. What's the earliest you can reach? If in that subroutine you can include visit at least one vertex of that color, then you would do it as part of this computation and it wouldn't change the ILP directly. But yeah, for just saying you want at least one vertex, one red vertex on your journey or no red vertex on your journey, I think this could still be solved in polynomial time.
That's a very nice side effect of this. I like it. Any other questions? Either, yeah?
So, I mean, you're looking for a temporal realization, and I assume for a given matrix there can be multiple solutions. Do all of these use the same number of labels? It's not obvious to me.
I mean, the thing is, of course, you could always add. Oh no, you could not always. I was just going to say you can always add labels, and it's still a solution. But adding a label could create a path that's too short. But yeah, I mean, definitely for some instances you could add labels. So if I go back to okay, I need to go back very far. But like in this, if the period is large, I could also assign labels 10, 11, and 12 in addition to 1, 2, and 3, and it would still be a solution. So you would want to look at minimal solutions. And my feeling would be they will not all have the same number of labels. So if you want to make it more difficult, you could not only say, is it yes, no, but among all yes, for yes instance, find a solution that uses the minimum number of labels.
That was my question, that because this looked like a minimization problem to me apart from actually seeing where you can do it, because you would want the most use the least amount of resources to realize this graph, which could be an interesting thing to explore.
I mean, I guess the FPT algorithm that we have for parameter n would probably work for this, because there essentially we enumerate all snapshots, right? All combinations of non-empty snapshots that allow you to realize it. So among all combinations you find, if you choose the one with the minimum number of time edges, that would also solve. So that FPT algorithm would also solve the minimization problem. Not sure about the other.
Okay. Thanks.
All right, I think we better draw to a close there to get swapped over in time for our next speaker. So let's thank Tom again.